completely different. I'm not atomic physics, but it is laser physics. So how many people here really consider themselves laser jocks? I know there's a couple. Yeah, 3, 4, 10. So that's what you'll want this to. So first, some references. I still like, even though it's really old, I still like our original LCLS Conceptual Design Report, Chapter 4, which is available on the web, which is a fantastic FEM tutorial. Some of my slides come from there. Margritando has written quite a few things on tutorial nature on this, and the person who is, the young person who's largely responsible for the FEL age from the point of view of theory is Zhirong Huang and his mentor Huang Jae Kim, and those guys have written on this too, so we can look at those things. So here's the outline. First, I'll say a little bit about radiation itself, how X-rays are produced, free electron laser basics, LCLS, and the growing list of X-ray FELs, but actually late last night I cut out the list of the growing list part because it would be too long. And then the future maybe, which I think, I hope, is attosecond X-rays with terrible per centimeter field strength. Okay, well, 1960, this is one of those Moore's Law plots, right? In fact, that's what this blue line is. 1960, a lot of stuff started to take off exponentially. We all know about Moore's Law. Here's that wonderful slope that makes everything in information technology possible today. Here are X-ray laser, or X-ray peak intensities, not laser, X-ray peak intensities. And you see we've been on a torrid path in the last 50 or 55 years, greatly outstripping Moore's Law in how much brighter X-rays are becoming. So why is that? Well, beginning, it was just X-ray tubes. And then we learned how to use relativistic electrons in bending magnets. This was the era of the 1970s and the beginning of the synchrotron radiation sources. We discovered if we started, this is a wonderful story here, I won't have time to tell about how we went from bending magnets to wigglers to undulators. It was amazing. The reason that it worked is politically, because these were all parasitic sources on high energy physics synchrotrons, but the reason that it worked is that it made the electron beams colder, so that it actually made them brighter for high energy physicists. So they went from forbidding slack scientists like Herman Winnick to put wigglers in the storage ring to insisting that they put wigglers in the storage ring overnight. So we went from wigglers to undulators and then finally to FELs. 10 orders of magnitude between the third and the fourth generation, sometimes called a factor of 1 billion, which sort of underestimates it, but okay. Now, let's start with some basic physics. This is all a basic physics talk, which you'll be able to, I think, understand completely, and by the end, you'll be able to explain and tell your friends why free electron lasers are so wonderful. So let's look at an accelerated electron. Acceleration in a circle, synchrotron radiation is just the radiation that comes from electrons accelerating in a circle. Of course, the acceleration is always perpendicular to the velocity in that case. And if the electron is going around relativistically, this donut-shaped radiation pattern that we're all familiar with turns into a narrow beam with an opening angle of 1 over gamma. That's the relativistic gamma. So if you have a bunch of electrons in such a device, they emit radiation with random phase, and if there are n of them, you then get radiation intensity that goes up like n, and the number n in a bunch can be as high as on the order of 1 billion or so. Now, one of the things that really got synchrotron radiation going, even in the bending magnet age, is that this radiation source becomes very powerful if the electrons become relativistic. It's kind of amazing how it scales. Here's standard Larmor, K equals 1 for CGS, 1 over 4 pi epsilon naught otherwise. And if you take this acceleration and write it down for a relativistic electron going around in a circle, it acquires this gamma squared, and of course it's squared, which means that the power radiated goes like gamma to the 4th power. So should we increase the energy of our relativistic electron beam by 10-20%? Yeah, every little bit. In fact, this tells you why the high energy physicists dropped electrons, because this radiation becomes a significant fraction of the energy circulating in the beam once gamma gets high. And so they needed to get to high energies without getting to such high gammas, and that was the reason. So that's it on bending magnets. You're now experts. Let's go to periodic magnetic structures. So here's the standard cartoon. These are permanent magnets. This is the pole, south, north, south, north, south, north. So you see the magnetic field is perpendicular to the direction of the electron motion, and then the force, and therefore the response of the electrons to this magnetic field is perpendicular to those two directions. So this is just the Lorentz force. It will wiggle back and forth. So such structures are called undulators or wigglers. Of course, what we're interested in now is the highly relativistic limit. So let's take a look at what's important. Of course, the electron energy is going to be important because that will, for one thing, determine the opening angle of the radiation beam that goes out there. It's the same thing as in a bending magnet. The wavelength of the light that comes out, the undulator period, are the two characteristic distance scales. The undulator period has to be something macroscopic because we have to be able to build it, although it could be something as small as optical, because the undulator could just be a laser field that's counter-propagating. That would work. But typically we use powerful permanent magnets with a few centimeter periods. The number of periods in an undulator is finite, so that number is capital N in here, and then there's a peak magnetic field, B naught. So the sort of first order thing is that there's a sinusoidally oscillating magnetic field. Here it is, and it's got a period of the undulator period. Okay? Now, an important parameter in this wiggling turns out to be how much it wiggles. So you could say amplitude, right? Let's see how much we deviate. But it turns out that the angle is a little bit more interesting. So let's consider in this sinusoidal motion the maximum slope of the sinusoid. Okay? So that's like the maximum angle of deviation. Since electrons are radiating in a direction that's more or less forward to their instantaneous velocity, just because of relativity, that angle then will tell us the angle of the radiation spray that comes out as a result of the wiggling. So K is the sort of normalized angle of deviation. It's not actually the angle of deviation. The actual angle is K divided by gamma. It's got that same 1 over gamma. So in the rest frame of the electron, which is going up and down like this, there's a relativistic shortening of the undulator, but in the lab frame, there's a relativistic flattening out of the wiggle. So K over gamma is that maximum deflection angle. So you can see, because we also have this 1 over gamma cone here for just the bending style radiation that comes out from a relativistic electron, you can see that there must be two important regimes. One, where K, this normalized K, is greater than 1. In that case, the radiation emitted on these beams actually falls outside this narrow cone 1 over gamma, so it'll radiate somewhat over a wider cone. Okay? And if that's the case, then radiation on successive bends won't generally add up coherently. And then the other regime is where the deflection isn't so large, it's within gamma, and in that case we have an opportunity for constructive interference. So in the under the right circumstances, we can get the power to radiate as n squared, and of course that's what we want. So this is the wiggler regime, this is the undulator regime. Physically these devices are exactly the same. You go from one to the other by changing the magnetic field, which you can do by changing the spacing, or by changing the energy of the electron beam, which is, I'm not even telling you how the accelerator works here. Okay? We've made those. Okay? Yeah?
Perhaps I missed it, but what is the physical significance of K?
K is the normalized angular deflection. So in other words, K over gamma is a physical property in the lab frame. It's the maximum angle of deviation of the electron. How do you control it? Well, you can see, you could control it by changing the peak magnetic field, which you could do by moving these magnets closer together, or we'd make it bigger. Because it depends also on gamma, you could change gamma. You could change the electrons. You could go from 15 to 10 GeV, for example. And K is a big deal. You know, These accelerator physicists, you know, we laser jocks, we have certain jargon that we just throw around all the time, and everybody knows that, you know, we say doubled, everyone knows what that means. We say red, everyone knows what that means. We say blue, everyone knows what that means. It doesn't mean what a standard person on the street would think. We know what it means. And these people use K, okay, all the time. Okay, so here it is again, K, same K. I said you could get constructive interference under certain conditions. What conditions are those? Well, this is the most fun slide. This is where, oh, I get it. The relativistic electrons are almost moving the speed of light, but they're not moving in a straight line. They're wiggling. So even though they're moving the speed of light, they aren't actually going the speed of light. They are progressing down the undulator slower than the speed of light by some amount, depending on how much they wiggle. Depends on K, right? Depends on K. They also aren't truly, really going the speed of light. I mean, they are actually just going nearly the speed of light. There's a factor of 1 over gamma there. So resonance occurs when the electrons slip one optical wavelength. By optical here I mean the radiated wavelength. One radiated synchrotron radiation wavelength, which I call lambda R, but actually someplace I call lambda 1, and I cut and pasted from Jerome's paper and used 1. I think it might be kind of a dyslexia thing, because we must have meant R in here. 1R. Anyway, so resonance occurs when the electrons slip one optical wavelength after each undulator period. Okay, so here's the wiggle, here's K over gamma. You can see what it is. And here are these guys going one period, they fall back one cycle. This is electric field down, up, down, one cycle. That's the resonance condition. Okay. And then you can get coherent addition over the undulator. You can get this n squared buildup. It becomes like a doubling crystal. You know, as you go, make it twice as long, get 4 times the amount of power, just from constructive interference with the field. Okay, there are 2 terms here. This one is the not quite going actually the speed of light term, and this is the unwiggling term. And since I showed you that K equals 1 is sort of the magic crossover to when you can start seeing this, you can see that you've got to include both these terms. They're comparable. Okay, so now we get to do all of this wonderful doing something periodically n times and adding it up coherently physics, which I think of as diffraction grating physics, or multiple slit diffraction pattern physics, right? It's basically just a diffraction grating equation. The electron slips one cycle per undulator period, so the length of a coherent pulse, the length of a pulse that you make, has to be at most n cycles long, where n is the number of periods. You slip one period every cycle. By the time you get out of the undulator, you've slipped n periods. You're creating a coherent pulse brain. Coherent means the phase at the front tells you what the phase at the back is. What is that distance from front to back? It's got to be capital N, the number of periods. So you've kind of constructed a pulse that has a certain length. Okay, that's called the coherence length. The highest field that is the best opportunity to get this coherent addition happens exactly on the resonance. Okay, so if you're not quite on the resonance, how does it go? Well, it goes like the diffraction grating. It goes like a nice little Fraunhofer thing. You can be very unlucky and get destructive interference over exactly adding up over the n periods, or maybe you could get unlucky in other places, but basically it falls off like this. Okay, now it's only a few minutes into this talk. Yeah, about 15 minutes into this talk, and I've already explained, and we already now know that the undulator resonance condition, that turns out to be exactly the same as the free electron laser resonance condition. They're the same. So now you know what color will come out. This 1 over gamma squared is the color that will come out. The undulator bandwidth, explained, just depends on how long the undulator is. Want to have narrower bandwidth, just build a longer undulator. The photons come out diffraction limited if they're within that cone, if you have a small k. So what's different between just the way an undulator works, which have been around since the mid-1990s, like the advanced photon source, is filled with undulators. What's the difference in an FEL? The difference is something having to do with coherence between electrons. Okay? So here, this tells the story. Here's the undulator condition for a single electron. Photons produced on different undulator bends, but from the same electron, are in phase. That's the condition that we just derived, okay? Here's the problem. Here's what my electron bunch looks like. These electrons are all in different places. The photons from different electrons are out of phase. A problem, right? Now, okay, maybe it's not a very big problem, because after all, each electron is going to be producing this really powerful burst of radiation, scaling like n squared, right? Unfortunately, not right. Undulators are actually weak radiators, so although you get this wonderful classical buildup, the number of photons per electron at the end of an APS standard undulator is about 1/100th of a photon. In other words, an electron goes through 100 of those, you know, roughly the number that there are on the whole ring, roughly, okay, before it emits a photon. One photon. So you aren't going to make a laser that way. However, there's this really interesting little thing that people in the field of radiation know because it's so important for microwaves, magnetrons, things like that. Okay? And that is that if you change the wavelength of the radiation, you can eventually get all of the particles that are in your bunch radiating to radiate in phase. And it's not very mysterious how that happens. It's basically the way a classical antenna works, where the current in an antenna has lots of electrons, right? They are not coherently related to each other. However, they are all within a small fraction of the wavelength of the radiation, and so they radiate in phase. It's just, that's a classical thing. A bunch of classical sources, they will radiate in phase under that condition. So here you get, for a bunch of electrons, you get to go from the power radiated by each electron times the number of electrons. You get to go to that amount of power times n squared just by changing the wavelength. And n, I said, was about, maybe I didn't say it was written there, it was about 1 billion, typically. You know, we talk about a nanocoulomb as a good, healthy bunch of electrons. We work with smaller amounts of, you know, a few picocoulomb, a few hundred picocoulombs. Not much smaller than about 20 picocoulombs. That's a very weak bunch for us. So that is billion, and that's a lot. N squared can be a lot. So how do we get this bunch of electrons to turn into a free electron laser? Well, we could make the wavelength of the free electron laser longer, and then, you know, then you get a microwave tube. Or we could get them to microbunch so that their density fluctuates, so that they're all lined up on successive cycles. And that's actually what we do. How do we microbunch? Well, here's the great thing. This is why, you know, this is why FELs happen. I mean, if microbunching was a really difficult technical thing, I wouldn't even be talking about it. Here's the reason that free electron lasers exist in this era, because microbunching happens by itself. It happens by itself. It's a self-organized thing. They will find a way to microbunch. Once they begin to feel their own radiation. This is where the quantum theory starts. You start thinking, stimulated. They're starting to feel their own radiation. This is where the stimulated comes in. So let's see how that happens. Okay, here's an undulator. Plus, minus, these are the directions of the field. Okay? Magnetic field. There's that undulator equation again. And here's the wiggling electron. Okay? Now, there's K over gamma, the deflection angle. Okay, now, let's say that the electron is coming along, and when it reaches this point where it's feeling a large deviation in its motion, the electric field is pointing in the same direction as the instantaneous transverse velocity of the electron. So the electron is going around, it's wiggling the magnetic field. There's also an electromagnetic field around from previous synchrotron radiations or of other electrons. And And it happens that they add up, the force adds up. So then I get a little extra pull at the point when I'm getting my maximum deviation from the magnetic field. Okay? Now, I happen to be in resonance. Of course, 1/2 cycle later, both of those have reversed. 1 cycle later, both of them have reversed again. Both the electric field of the radiation and the direction, the transverse direction, is not going to reverse. They stay in phase, and therefore you get coherent addition of the force exerted by the radiation itself on the electron. Okay? Now, what I've actually described is loss. You thought I was describing gain. But I've described a situation where the electron gets more energy from the field. Of course, that's loss. We call gain when the field gets the energy. But you could have the opposite situation too. Some electrons lose energy, others gain. And so the energy is modulated at the resonant frequency. Some gain, if they're in a slightly different place, they happen to lose. And so at that resonant frequency, you get a modulation in energy. Okay? Now, here's the really cool thing about this response. I explained to you that the electrons are all going the speed of light, or as close as hardly makes a difference. That's true, but they're not going in a straight line. So what happens when they get this extra kick is they start changing their orbit. Well, once they change their orbit, they start lagging behind or leading the resonance. It's a little bit counterintuitive, but if I kick it a little harder, it'll make a larger orbit, it'll come back later, it'll lag the radiation. It'll start to lag behind it. On the other hand, if the electric field was countered, then I kick it a little bit less hard, or I counter the motion of the magnetic field, it'll undergo a smaller orbit, and then it'll come back center. So there's this lagging leading stuff that leads to micro bunching. The actual density starts to bunch up every cycle. Okay? Micro bunched beam then will radiate coherently once it gets micro bunched enough. So in a free electron laser, you have that situation where electrons eventually get bunched and then they start radiating. And in a simulation, which I'll show you a little bit better example of later, you can see this happening in the density in the co-moving rest frame of the electrons. That's the resonant frequency. And the radiation intensity then should go like n squared for n, the number in the microbunch. Okay, so now that you know the basic principles, let's look at how we can turn it into a laser that we can use. Well, the original way that John Mady, actually this was invented at Stanford. Did I neglect to mention that? Long time ago. By Mady, and his original idea was, well, he's a laser guy, right? His original idea is let's put in some mirrors and let's build a resonant cavity where the cavity resonance matches the FEL resonance, and we'll get alpha radiation. That's certainly one way, and that way worked at Stanford for areas where you had good mirrors and good control over the cavity. You could also just build a seated amplifier where you input radiation that you made some other way, maybe this way or maybe just with the conventional laser, but it happens to be on resonance and it gets amplified. Or you can just make the undulator really, really, really long. If you do that, then the radiation that you produce that's just spontaneous undulator radiation at the beginning of a very long undulator will start to kind of build up, and if it happens to be at the right color, right in resonance, it'll start to build up coherently and take over. That process is something that we in the laser business have forever called amplified spontaneous emission, or ASE, but the accelerator people decided that they would call it self-amplified spontaneous emission, or SASE. So you can tell whether you're talking about X-ray FELs or any other kind of a laser by whether you include or drop the S, but it's the same. It's the same thing. And notice that this doesn't require input radiation or mirrors, so it's very good for X-ray regimes where you don't have good optics. Okay, so a few other little nuances here before I get to the actual. some electrons accelerate at every cycle, and when they accelerate at every cycle, that's loss, because it's loss of X-ray power. Some decelerate at every cycle, that's gain of X-ray power. Okay, and so you've got to balance loss and gain, and you would rather have gain win. That's your gain. Your goal is to have it be gain, not loss, right? Not both. So gain is a trade-off between detuning and spontaneous undulator power. So what you would really like is electrons to naturally move towards the resonance as they undergo the FEL process. That would be better than if they started on the resonance and then either gained or lost after that. So Mady's theorem is exactly that. Don't tune on resonance, tune a little off. Not all the way off this curve, about halfway off. Actually, if you take the derivative of this curve and look at the peak of the derivative, that's the best gain. Okay, now let's talk a little bit about this bunching process and how it gets started. Which electrons are going to be the ones, the lucky ones, that happen to be responsible for seeding the microbunching, and which ones aren't? Well, this depends on where the electrons are. The kth electron produces a field with its own particular phase, and then those fields just superpose. So I could add them. There they are. They're just added up. And there's a whole bunch of them, so I'll divide by the number of them and create a dimensionless parameter. This is called the bunching parameter. If the bunching parameter is 0, it means that my electrons are perfectly uniform, and the fields add to 0, and it's going to be really difficult to make a laser. If B equals 1, they're perfectly bunched. There's constructive interference, and I've already made a laser. If B equals in between, they're randomly distributed, and that's the normal for us, for a normal situation for FEL SASE operation. The undulator radiation starts up from noise. Noise means just the random fluctuations that produce spontaneous emission of undulator radiation in the FEL. And then the modulation of energy gives rise to modulation of density. You have an exponential growth phase, and eventually you get really good microbenching, and then you get saturation at sufficiently high power. And here's a simulation by Sven Reicke at UCLA that shows this in the co-moving frame. Those electrons are being in the process of going through a long undulator and being bunched. You can see it happening now. They are microbunched. Now look, they start to kind of trail off on one side. You see that? What's that? That's...
So the vertical motion is the...
the vertical motion is because it's a true 3D simulation, and you have to put in focusing quadrupoles every so often to keep the electrons.
So that's the wiggling motion.
So that is not the wiggling motion. The wiggling motion you can't see; it's too small. The big breathing. I'm sorry, I should have said the big breathing. Don't worry about it. It's part of the simulation. It is something you have to worry about in beam physics to keep the beam together. Okay? But the main thing you have to worry about is what's happening longitudinally. And they are starting to bunch because some are getting sped up and some are getting slowed down through this wiggling. And then when they get maximally bunched, you get a big burst of coherent radiation, and the electrons all lose energy. It is not a small interaction anymore. I said that undulator radiation is weak radiation. You hardly notice that the electron changes its energy when it radiates 1 photon, 1 kilovolt photon, and it's a 6 GeV electron. Okay, but this collective effect is so large that all of the electrons begin to lose significant amounts of energy. You can even see that in the simulation.
So does that mean their repulsion becomes more important?
No, they're so stiff. These electrons have effective masses with respect to electron-to-electron repulsion in the lab frame of 30,000 electron masses. So no, and they get through the end of it pretty fast. Okay, so here's a little simulation done by some of those people, Zhurong and company, and you can see the exponential growth regime. This is for LCLS properties, and you can see the saturation. This is power on log scale. Every decade is pretty close together, so it's a huge increase. What's more interesting is to look at how the microbunching affects the light. Now let's take a look at the spontaneously and stimulated emission coming from the end of the undulator. If you looked right here, if you stopped your undulator right here, it would look quite random. And this scale here is timed in femtoseconds. 0 femtoseconds is here, 1 femtosecond is way over here, 2 femtoseconds way over there. So this is a 2.5 femtosecond scale. If you go into this exponential regime, you begin to see that the organization of microbunching has led to certain the cooperation link, how long can electrons move together before they forget their phase. And that gives rise to a burst of radiation that's a certain length. Well, I am looking in the time domain here, so it's that length. Okay. And at saturation, that's preserved. So the SASE production of very short spikes that are on the order of a femtosecond long or so is a natural outcome of the microbunching phenomenon. So this is a born to be ultra-fast source. Okay, the best conditions for SASE, of course, is that the electron beam and the X-ray radiation have to match in Rayleigh range, and they have to be tuned right to be able to match this Meade criterion. So you can't have a spread in electron energies that's too much. So this means you have to have very good electron beams. Good in the sense that you better be able to focus them really well. That is, they have not very large transverse emittance. Their emittance is really small. And the other thing is they better be pretty monoenergetic, pretty much, in order for the free electron laser to work well. So I know I'm going to go into a practical realization of this. So any questions about, are we experts now? How many feel that, okay, I get it now? Yeah, there's a couple. You probably do, even though you don't feel that way, because not that, it's all there is.
Again, this breathing motion, you're saying that's artificial? Or is
No, it's not that it's artificial. It's that we're looking over a very long distance. And over that distance, there is a natural divergence because of the emittance of the beam that they correct for with quadrupoles every so often in the simulation. So that's not the single oscillation.
What gives you saturation at the end?
Pardon me?
What gives you saturation at the end?
The electrons all start radiating coherently, and therefore they lose energy, and therefore they're no longer in resonance.
Okay.
That's it. And you can fix that by gradually tapering the magnetic field in your undulator beam. Keep them in resonance. People do that. We do that at LCLS. We do that.
So you mean the microbunches don't stay microbunched? They just form microbunches, radiate, fall out of resonance.
Well,
okay,
they form microbunches. They radiate. Now, question: do they fall out of resonance? Well, they do if you don't change your undulator parameters, because they've lost energy, so now they have lower energy. If you want to keep them in resonance at the same undulator period, you've got to do something to compensate for the fact that they now have lower energy. If you do that, then they'll stay in resonance.
So, Phil?
Yes?
So is it safe remark to say that the L in FEL is the bunching part?
Yeah, the microbunching is the thing that leads to the coherence, and therefore it's what we call the laser. There is a quantum theory of this, which is sort of the same relationship to the quantum theory and the classical theory for things like magnetrons and in fact, I think of this whole gigantic kilometer-long structure as a kind of an artificial atom that has a real level structure that's given by the beam parameters. And then you can define stimulated emission. So Meade actually spent quite a few years writing, after we understand, we all understand this in the same terms today, and everybody, this is the way it's all taught, and we all understand. But there's a quantum theory for this, of course. There has to be. Quantum mechanics rules, right? We're atomic physicists, we know that.
But has any quantum effect been seen?
Well, it depends on what you mean. I mean, the spontaneous fluctuations that give rise to SASE are quantum effect.
Okay, those, yeah. But the emission itself just...
Well, it's like any coherent laser. Okay, so you're a quantum optics guy. Any coherent source of radiation. Okay, it's over there in that little coherent bubble. Okay, So can we squeeze it? Well, you could play all of those kinds of games, I suppose. So you could, in that sense, you could say you're doing quantum mechanics. Yes?
So in Jackson, at the end of the Jackson book on electromagnetism, they say that the classical theory of like radiating the electron and absorbing its own radiation is unstable, so you get like accelerating the electron. So like in this physics, those things are important. So how do you describe them?
I can't, since I don't have a picture of what's at the end of Jackson's book in my head, so.
Okay, it's like, it assumes a finite electron of finite radius in classical picture, and when it emits radiation, it reabsorbs it, and it gets self-accelerating, and I don't know, he doesn't...
He may be more trying to describe things like the self-energy of the electron. Honestly, I'm kind of at a loss here, but not having that chapter in front of me.
Okay.
As if he's talking about things like the self-energy of the electron and its spontaneous emission and reabsorption of, is basically its field, what its field looks like when you get very close to the origin. And no, this is quite different from that. But I'm not sure if that's what he was.
So it's like classical picture that
This is quite. Okay, Google Earth. Everybody uses Google Earth. There's the Slag's Linux. This is the building. The building itself and the roadways alongside it are visible from outer space. There's the horse park at Woodside. There is the Stanford golf course. There is my house. And LCLS, yes. LCLS, the experimental areas in the undulator are underground, but they're right here. Okay? So you get the idea. We use the last third of the Linux. So this is 3 kilometers long for reference. The last 1 kilometer is used to generate the electrons for the undulator. And here's what the undulator looks like. It's 133 meters long. It's a tunnel. And it's very straight. And it's actually made in sections so that you can move things around, taper, all of those things that we've been talking about. And here is that exponential gain curve in saturation from the very early running. This is 2009 in April. This is probably from the first week of running, possibly the first day of running of LCLS when it first turned on. And here's what the beam looks like on a YAG screen, rendered in MATLAB. So it's a beautiful transverse beam coming at the end of this thing. Wavelengths can vary between on the order of an angstrom out to a few tens of angstroms. Photon energy that corresponds to goes up to 10 keV. Pulse lengths can be as short as that single spikes that I showed you. They're conservatively calling that 5 femtoseconds, but in the simulations you can see it was even shorter. Can go out to more than 100 femtoseconds. Soft X-rays you can actually get up to 500 femtoseconds. Pulse energies are up to several millijoules, so this is like it's like a quantum ray except 10 kilovolt radiation. And it's up all the time, but only for one user or two maybe at a time. Now, a little bit of the secret sauce that makes the electron beam so bright, because I pointed out that that's really what makes it work. First of all, you may have noticed from outer space this doesn't look very much like a synchrotron. I don't know, it was the first thing that occurs to me, like, what happens when the electrons get to the end? How do they get back? And the answer is they don't. They don't. They're dumped. All that energy, dumped. Except for a little bit goes into the free electron laser. The rest is dumped. Okay? Makes it rather energy inefficient, not a very green machine. But it means that it doesn't have a lot of spontaneous emission of radiation heating up the beam. So you can keep the transverse dimensions of the beam very cold and keep it very bright. That's important. And in fact, it's not even quite enough to keep it very bright and cold. So there are these extra sections that are bunch compressors. And if you're a laser jockey that does ultra fast, you will exactly know what's going on here. When this is the electron bunch traveling down the accelerator, and I'm expressing it in kind of a funny units. This is kind of a phase space picture, where this distance is the distance in the bunch, front of the bunch, back of the bunch, in its co-moving frame. But this transverse distance, this is the energy spread of the beam. That's what I'm showing, kind of a phase space thing. Okay, as the electrons go through the undulator, goes through the accelerator, they acquire a chirp. They actually acquire a chirp even in vacuum. because there is some Coulomb repulsion. The front ones feel the back ones, and they get pushed forward. That doesn't mean that they go farther because they're all going the speed of light, but it does mean that they gain energy. And the ones in the back lose energy, and so you would develop a chirp. There are other reasons for the chirp too that have to do with the walls of the cavity. And that chirp is really cool because, as we know from the ultrafast laser game, once I can put a coherent chirp on my long pulse, I can compress it to a shorter pulse. And I do that with the prism compressor. And that's exactly what happens at LCLS. In fact, they increase the amount of chirp by accelerating off the crest of the traveling field that's accelerating all the electrons. All the electrons aren't even seeing the same field as they travel along because there's an S-band, a couple of gigahertz RF field that's accelerating all the electrons, and the ones at the back see a little bit less field than the ones in the front as they move along. So you get quite a chirp. Go through a prism compressor. This is just bending magnets. The redder electrons take a longer path. The bluer electrons, red and blue in the laser jock sense, take a shorter path, so they bunch. You can compress it. And this happens a couple of times at LCLS. In fact, let's see. Oh, that's right. In fact, you can see where the bunch compressors are. There are 3 of them. 1, 2, and 3. This one isn't a full bunch compressor because it has a second task. Its second task is to keep super high energy gamma rays from beam gas collisions and wall collisions from saturating the downstream experiments. So they deviate a little bit. Okay, FELs for harmonic radiation. Okay, the FEL gain creates a density modulation, but that means that you can also be on resonance for harmonics. And they're weaker, but they're not so weak. So LCLS actually does produce about 100 megawatts in the third harmonic, while it's busy producing tens of gigawatts in the fundamental. Now just a few tricks. Early on, possibly Linda's run, but maybe the next one after that. They discovered that if they go to smaller charge, it was predicted first, and then it turned out to be true. If they go to smaller charge, you can make fewer sassy bursts and make a shorter pulse. That works really well. So typically, when we're trying to do ultra-fast stuff, we'll work with not a nanocoulomb, but only 20 picocoulombs. In soft X-rays, a low charge mode, and then we can get on the order of a few femtosecond pulses pretty reliably. Now, let's take a look at this bunch compressor again. And let's look halfway through. Some of you may be old enough to remember the old coherent control days when we were all doing all kinds of stuff with pulse shapers. I don't know, how many people here know what a pulse shaper is? Okay, you do, right? Old people, some of the younger people kind of do. So in a pulse shaper, it's just a compressor where halfway through, it's a one-to-one compressor where you've arranged to have no net compression, but halfway through, you have basically your spectrum spread out transversely, and you can put in a filter there to get some colors to pass and others to be delayed and whatever you want. Well, same thing happens with the electron bunch here. So we get this nice chirp in the middle of the bunch compressor, and this gives us easy access to the time coordinate along the bunch, and we can use that. We can put in a little foil it essentially does the same thing as a pulse shaper does. It messes up the trajectories just a little of the electrons that have to go through the foil. These electrons are ultra-relativistic. They can pass through thin things. But the electrons that go through the slot don't get affected. And so the unspoiled electrons are the only ones that will be able to laze. So you can also make short pulses that way, and you can move them around in the bunch. So 2 femtosecond full width half max pulses are sort of commonly made in this way. And you can have 2 slots, and you can have slots that vary in width, and you can have a V-shaped slot that varies, 2 slots that vary in their position. So now we have full control over 2-pulse operation with separation and pulse duration, and now you can really go to town with trying to do ultra-fast experiments using this tool with a simple slotted spoiler. So that's actually in use now, and it's used by a lot of groups, particularly the atomic physicists. So that's one trick. I'm just going to show you a few tricks. Yes?
About the slot versus the gas, what's the relative pulse energies you can get? Like, so if you short using a gas chamber versus this, is one way better than the other?
If you,
Or
tell me about the gas chamber.
the way you described before that to go, before the pulse shaping way to go to the short pulse.
Oh, by just having fewer electrons,
Yeah.
a smaller bunch. It's quite comparable, because actually what you're doing is quite comparable. That is, what you're doing is you're restricting the distance along the bunch where the emittance is and brightness is suitable for lasing. The difference here is that, well, you have to add an extra element, so that's a kind of a complication. That's one thing, but also the ability to have some physical element that is determining how long that bunch is. That's the difference. Okay, here's another trick. This is kind of a cool trick because it relates to something that Ken Schaefer mentioned yesterday. So I wanted to put it in. We can do hard X-ray self-seeding at LCLS. Hard X-rays are X-rays that can diffract from solid crystals using Bragg's law. Okay. So here's a diamond crystal. Diamond is pretty cheap these days, single crystal diamond. And X-rays can diffract from the diamond and not really absorb it very much. And so we can use that to create a very narrow band version, filtered version of the X-rays. Okay, and how does that work? It's interesting. I wouldn't even have mentioned this because it's commonly used, but it's just one of the tricks. But it works in a way that looks very much like a picture that Ken Schaefer showed. The idea is that if this is set up for Bragg scattering, then the X-rays that happen to be obeying Bragg's law will scatter from it instead of going through. They'll see a big attenuation, and so you'll get a notch, a spectral notch in whatever the spectrum of FEL radiation is. You'll just have this notch. Okay, question, what does that look like in the time domain? It may not have been very obvious to you before yesterday, but Ken showed you that in the time domain, it looks like a ring down cavity, right? So there is this trailing, there's this little minimum, and then there's this trailing stuff which needs to coherently interfere with everything else to get a narrow notch. It's the only way you can get a narrow notch, right? Well, it's delayed by about 20 femtoseconds for something that's as good a Bragg scatter as diamond. So if we delay the electrons by 20 femtoseconds, and then send them through a second undulator, they'll just be seeded by this downstream stuff, and you can get a nice narrow band tunable radiation. And it works. It works really well, and it's in standard use now. Okay, here's the evidence that it works. Here's the spectrum from a SASE pulse. Well, all of this little structure here is because all of the microbunches have their own color. They're all self-organized. They weren't talking to each other before. Here's what happens after the diamond crystal. That's the spectrum. One bunch, then one color. And this is much wider than one of these bunches because it's set by the bandwidth of the diamond, and you can tune it around. It's cool, very cool. Really love that. Half an EV flip. Okay, other ways of seeding. Another way of seeding is high gain harmonic generation. This is used actually at the Fermi free electron laser in Trieste, not used at LCLS. But it was developed at Brookhaven, and it's actually a very powerful technique. The idea is from those harmonics, since amplified radiation in a free electron laser also has this harmonic content, you could send it through another undulator that actually is intended to amplify the harmonics, and you can bootstrap up to shorter wavelength that way. This also works. And then finally, and this really is kind of finally, I could give an entire second talk on all of the ways that you could use a laser beam to condition the density in the electron beam before it goes into the undulator. Now, the reason this is so appealing is that that electron bunch is going the speed of light, and so is light. Light also goes the speed of light. So I can merge a laser beam with the super relativistic electron beam, and they will co-propagate a long distance. Every electron will just, depending on where it is, either see a transverse electric field that's giving it momentum this way, or if it's a half laser wavelength later, this way. And these laser wavelengths might be 1 micron or a couple of microns, and so that's a pretty significant number of electrons then that get modulated in these modulation bunches. You can then turn that into a kind of way to see the laser. There are many papers on this, many simulations showing that this is a great way to make femtosecond pulses. And this is something that at LCLS2, I'm very, very much hoping this will be much more of a mainstream part of the research program. Okay, so here's my summary. My summary is just this slide. My summary is that now you know why you see sometimes these very, very dense log-log plots where this is photon energy from lasers all the way up to hard X-rays. And this is peak brilliance, which is the brightness of the light over 15 orders of magnitude. And the FELs are always way up here. And now you know why. Thanks very much.
I don't know about you, but I learned more in this 1 hour about FEL than I did since reading the original paper by Pierre.
Oh, that was the intention.
So, questions? Surely.
So I have a question.
Well, yeah.
Is there any thought about putting 2 mirrors to make it into real laser?
Well, yeah, there is. So I guess I talked about Pointier's thing, right? So of course, we went to a lot of work to make a very high brightness beam because you needed that to get above the threshold for microbunching and overcome the noise. And that's the reason why free electron lasers don't exist at synchrotrons, because the electron beam is just too hot, you can't make it cold enough. However, if you decided to take the effort away from the electron beam and put it into the cavity, the optical cavity, maybe you could just make a low gain cavity with a very high finesse, very low loss going around in a circle. Okay? Now you might think that that's very difficult in the X-ray regime, but actually it's not necessarily so difficult because Bragg mirrors, once you get to hard X-rays, Bragg mirrors are highly efficient. The loss from a Bragg mirror can be 10 to the minus 4, really small. So if you can have only a few of those mirrors and say build a ring cavity, you could get less loss than you get in the gain going through one pass of an undulator that's fed by a synchrotron, even though you don't get much gain. You could still overcome the loss in the cavity. And after a while, it would build up and it would lace. Okay? Ponthier Kim had this idea. It was like the original idea for FELs. I mean, the paper that he wrote with Jerome and all this stuff back in 2007, and probably before that, he's been very, very interested in pushing that. He's an argon theorist, accelerator theorist. And they are still pushing on it. And the feeling is that the ball may be advancing down the field just a little bit more recently because there may be a little bit of bandwidth in the system to allow some testing of this idea. So there's a workshop coming up that will use, it's called FELO, Free Electron Laser Oscillator, because now it's an oscillator that we'll talk about all the ways to do that coming up in March.
So if I build that cheap,
well, for one thing, if it really worked well, you could take any sector in the 36, right, sectors at APS, 39, 35 sectors at APS, you could take any one of them and turn it into a free electron laser. That would be kind of cool. Well, just, one beam sector at a time, that's the key. So you don't necessarily interfere with any of the other great uses for synchrotrons. It's a resource management problem now. even, well, it's still a physics problem because they haven't demonstrated it, but it becomes a resource management problem. And maybe the resource management people are getting a little closer to thinking they could do this.
So at the end of the beamline, are there many experiments or only one experiment?
Well, originally there was only one experiment, and there now is a lead experiment still, but as many as possible experiments are done in a parasitic mode, where if you're willing to use the beam that the lead experiment needs, and they haven't eaten it all up because, or you don't eat it all up, either one, then you can do it. So an example is, I don't know, Linda, did you talk about crystallography at all, nanocrystallography or anything like that? Sort of. So Linda talked about structure determination using serial femtosecond nanocrystallography, which means you drop little nanocrystals into the beam. They don't use up much of the beam. You could use the beam again downstream. Do a second nanocrystallography experiment, completely different sample. So that's now being done. And there are as many examples like that as possible in order to increase the number of users at one time. Of course, what you can also do is fan out the pulses. You know, if it's running at a high enough rep rate, this was the original idea of the Berkeley machine, which is now not going to be built, but there will, in the future, probably be those kinds of schemes too to increase the number of users. It still can't compare to a multi-kilometer circumference ring of synchrotron electrons that can have a beamline, every 10 degrees around the ring. It's really hard to compete with that. But this radiation is so much more intense that the applications are quite different.
In principle, is it possible to go to gamma ray with this free mechanism?
So the scaling of the parameters like brightness to get above threshold starts to become quite difficult. Possibly a way to bootstrap that would be to try to use harmonics. If you could build a free electron laser that had very much higher harmonic content. But that's the real difficulty. It's kind of interesting. When the FEL first turned on at LCLS, they tried to turn it on first at the highest energy. That was considered a conservative move because it was presumed that everything wouldn't be aligned quite right. And the X-ray radiation for hard X-rays is rather less destructive to the undulator magnets than soft X-rays. The absorption is different. And besides, it wouldn't laze anyway because the lasing condition, everything has to be just perfect. So while they're tuning up, they wanted to tune up at the highest energy. Well, it turned out that it lased within the first 45 minutes at the highest energy. So they kind of I wouldn't say over-engineered, but they'd engineered it so much according to having it match their specs that it actually just worked the first time they turned it on. And as a result of those kinds of engineering precisions, they have been able to push the energy up quite a bit above the original design highest energy of the machine, but not an order of magnitude. That's not going to be possible. There's plenty of room in the accelerator. That is, you say the accelerator's working at up to 15 GeVs, the highest energy electron beam that's used for LCLS. And they're not running on all cylinders yet. That is, they can accelerate the electrons more if they needed to. Yes?
Years ago, when you gave talks about LCLS, you emphasized how spiky the pulses were. You didn't mention that.
Well, I did. I showed the set. I did show the set. But I concentrated on how each individual spike was a coherence length. But the coherence length, that's only a couple of femtoseconds. So how many femtoseconds are there along the bunch? I mean, dozens, or many. So there are a lot of spikes, and they're in a different place every shot. That's a big challenge for us. That's true.
You mentioned that when the electrons lose energy, then you have to modify the ondulators so that they stay in resonance. So do you change the magnetic field, or?
Well, you could. What happens is you change the gap. The magnets are permanent magnets. They're very precisely aligned. They're really real micron precision. I didn't mention this. This is really important. The gamma squared scaling. So I have an undulator that's 3 centimeters period, and I get X-ray radiation. How is this possible? Well, it's just because it goes like the undulator period divided by gamma squared. Where did you get gamma squared? Well, it's really simple to explain. In the electron rest frame, the undulator is shortened by a factor of gamma. So it sees a periodicity that's much faster, and therefore